let's talk a little bit more about how to make things animated. So that was pretty cool, what we did last time. We'll bring it back in, I'll copy it back in, and we'll talk about it a little bit. But let's go to that piece of code, because I need to explain to you a little bit better about why we got animation out of that program that I made last time. It was a complicated program, wasn't it? So let's go to idle, and then I'll open the program from last time. And I'll just copy it into a new folder for today, just in case I want to change it. So this was the old file. It was bounce.py. I'll copy it all into a new file. I'll save that in a folder for today. And that will be, I assume, lecture 25, right? Is that the right number? Yeah. So lecture 25. And I'll call it, I guess, bounce copy. So this is a copy of what we had before. I can close the old one, but here was the program doing all its fun stuff. And when we ran it, we drew a rectangle, we put the ball in a random spot, and it started bouncing up and down magically. And the place where the bouncing occurred was in this forever loop, this infinite while true loop, while forever, until the end of time. Just draw a new frame, please. And I told you a little bit about animation last time, right? To animate a movie, you show a frame on the screen for a little bit of time, and then you change to a new frame, and then you change to another frame after that. How is that happening? Because I'm not saying anywhere in draw frame wait a second, keep it on the screen for a while. Why is that still producing animation? So let's get into that, right? Because that's a little weird, I think you would imagine, right? Because in theory, if you think about it, this could be true, right? If the program just keeps drawing frames and it never stops for a second to show the frame that it's drawn, maybe it's just going to keep on drawing new frames, or thinking about drawing them and never actually draw them, or just draw them so fast you don't see anything, right? How does it actually produce animation where it shows the ball up there, down here, down there? How do I get there? How does that happen, right? How is animation actually happening right now? All right. The secret is in the pieces that we're using in draw frame. All these things, this addition, this if statement, this other if statement, this go-to line especially. Each of those lines, when you run them in Python, they take a little chunk of time. It's a tiny bit, but it adds up. So programs aren't instantaneous, right? They take a couple milliseconds to run this line. .goto takes the longest because it's actually moving things on the screen. But that's the secret. That's why we're producing animation right now. So there's it takes a while to do that .goto in addition to everything else in draw frame. It takes a few milliseconds to produce the effect of all that code, to run it all, execute it all to completion. And while it's doing that, it's not changing what's on the screen, right? And so it secretly is showing you something for a little while. You just don't really have control over it. Does that make sense? That's the secret. That's why we are, we're taking a little bit of time in between each drawing, though we don't have control right now. And that's what produces animation, okay? So it's a little different to, the film reel where, you really are showing this frame for 1/24th of a second. Exactly. You're showing this frame for 1/24th of a second. Exactly. This frame for 1/24th of a second. Exactly. For this, it's kind of just however fast Python can run these lines. And so technically, if you run the same program on the computer in front of you, the giant one, I'm running this on my little puny laptop, it might move the ball faster for you. Does that make sense? Because it's running these lines a bit faster on your giant beefy computer with faster processors. Okay? So that's the secret. If you wanted more fine-grained control, there is a function in the time library in Python. There's a function called sleep. So I'll show that to you. Python time. There's a time library. And it can tell you what time it is right now. And there's also a function in it called sleep that takes a number of seconds as argument, as the single argument, and it stops the program, pauses the program for that many seconds. So you can be time.sleep 1.5, and then the program will wait 1.5 seconds before continuing. So maybe I'll show that to you. Why not? Let's see if we can have some more fine fine-grained control. Import time. You still have to like subtract however much time it takes to do all this, and like you can time that. You can use the time library to time how long this took, and like subtract it from how long you really want it to take. So that's totally possible. So let's be like, I don't know, just actually sleep. If I imported time right there, now I have access to time.sleep, and so after every frame, like do all the stuff and like make sure to just pause and show it there for a little while. Like I don't know, what's 1/24th of a second. You could do that. You could make it even choppier by like 0.1 seconds in between every frame or something. So it's like 10 frames per second at a maximum, because it's going to take a while to do all this already. So let's watch that work. So now every time it draws a frame, down at the bottom, it's going to pause for a second. And so now you see the choppiness. That's pretty fun. So now we have more control over like the speed at which our frames get shown to us. But like all this other stuff, it took a certain amount of time. We didn't really have control over it. But if you want to pause for a little while, stop the program for a certain number of seconds, then you're guaranteed to have whatever you just drew onto the screen shown there for at least 0.1 seconds. Does that make sense? It's a fun little idea, I think. And so, yeah, it's like an interesting animation now. If you want it to move at a normal speed, you'll have to like change the offset to something much larger, right? Like -15 or something. This determined the speed, didn't it? Whee! So now it's like old school. Kind of looks fun. I don't know. It's up to you. But like that's more fine-grained control now. But I kind of like it better the other way, where it was just like taking as long as it needed just to do it right, as fast as possible. That's a thing. That's a thing you could do. And I hope that makes a little bit of sense. That's why we get animation, because all this stuff from before really was doing the right thing. Really was taking a little while and making it work. All right, so yeah, if we're good, I'd like to enhance the program that we made last time, because balls don't really bounce like that in real life, do they? When you drop a ball, that's the best way I can draw it. It's like when you drop a ball in real life, like from the top of a building or something, it moves slowly the second you drop it, but it starts speeding up as it gets closer to the ground, doesn't it? And so it like bounces like this. And then it like gets back and slows down as it's getting the top of its bounce. Woo! Something like that. Woo! Woo! And like it starts like finishing itself, like it doesn't like eventually, right, it stops bouncing altogether, but it like speeds up as it's getting closer to the ground and like slows down as it's going back up. Bounce, 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 and that starts dribbling, right? So let's introduce that into our program. Let's model the real world. So like when you drop the ball at the start, it should be moving very slowly, right? Because gravity hasn't had too much time to affect it yet. And then by the time it gets closer to the ground, right, it starts moving a little bit faster. It takes less time to go the same distance, right? And then the second it hits the ground, like that's as fast as it possibly could be going. That's super fast, assuming no air resistance. It's like the fastest it could possibly be going the second it hits the ground, right? It's speeding up as it's going down. So let's remember this. So I think at least we learned about physics a little bit in grade school. Maybe we haven't taken a physics class yet in college, but let me teach you the process that we're going to model in the program. It's going to turn into just a few lines of code that make it work. It's going to be really cool, but let's learn how to model it, because we got to like introduce physics into our ball balancing program. So it's called kinematics, right? And that's the study of like how things move. So right now, if we want to use the technical physical words, our ball, when we bounce it, it moves up and down with constant velocity, right? That's the fancy term. Remember that velocity means how fast your position is changing. It's delta position, right? The change in your position, all right? But that's not really what happens in real life. The ball speeds up, right? It should be speeding up on its way down, and that means its velocity changes as time goes on. So that has to do with acceleration, right? Acceleration is change in velocity. So the question we want to ask is like, how fast does a ball change its speed? And that word we use to talk about the change in velocity is acceleration, right? That's change in velocity. Hopefully you've heard those words before, right? And the secret is, the answer is, at least on Earth, if you're close to the surface of Earth at least, it's gravity. Gravity is bringing the ball down and it's accelerating it by the constant g, right? That's the 9.8 meters per second squared. That's the acceleration due to gravity, yeah? So in real life, you drop a ball, it's affected by gravity at a rate of 9.8 meters per second squared. And the squared, hopefully that makes a little bit of sense once I say something, meters per second squared, it's just like it's dividing by seconds twice. It just means like, all right, the ball speeds up by 9.8 meters per second, right? Change in velocity per second, every second. That's why you get squared, second squared. The ball is changing speed by 9.8 meters per second every second. That is delta velocity for you, okay? So that means, like, gravity, you give it a little time to work, it moves the ball a little bit. That's one chunk of time. And then the ball has been speeding up, right? Its speed is increasing the longer it's falling. And so in the same chunk of time, you keep the ball falling, like let's say that's the same chunk of time, it's fallen more of a distance now. If you wait the same chunk of time, it's being pulled faster and faster. Acceleration due to gravity is affecting the speed of the ball, right? Hopefully you've heard those words before. But that's pretty much what we're going to program, right? So every time we draw a new frame, because we have to bring this back to our program now, right? Every time we draw a new frame, we need to let acceleration affect our velocity, all right? So it's not going to be like 9.8 meters per second squared. It's going to be like 9.8 units per frame squared or something like that, because that's how fast it moves, okay? So we'll just add a variable for all this stuff. So like acceleration is a constant, right? We want to model gravity. That's a constant acceleration. We'll just make an acceleration variable for the ball. It's like, all right, it's moving at negative 9.8 meters per second squared, or whatever, 9.8 units per frame squared. And then we'll also have a velocity variable, okay? And when you drop a ball, right, initially, it's not moving. So initially, its velocity is 0. But each frame, each time tick, we want to have it affected by acceleration. So just like, all right, right now it's 0, but after a tick of time, like, let's have acceleration affect the velocity. So now it went from 0, like you added in, to negative 9.8. And then you have it affected again, right? The next frame. Now it'll move a little bit faster. It'll go from negative 9.8 to negative 19.6. Yeah? And you just keep doing that. You keep having the acceleration affect the velocity until it hits the ground, at least. All right? And so that's going to be the goal. That's what we're going to program, okay? So I think that's all that I wanted to say. Does that make at least a little bit of sense before I code it up? We're going to make a constant acceleration variable and have it affect our velocity variable, all right? And our velocity variable is already here. We just called it offset, right? We just called it offset. That's really your direction. That's how fast it's moving. So each frame. So that's what we're going to affect. That's what we're going to add. And yeah, that's pretty much what's about to happen. So just we'll also have to deal with bouncing in just a second. So I'll draw that on the next slide, but we'll get there. We'll get there. I'm going to copy all this into a new file, and this will be called bounce with gravity. So let me get rid of all my time.sleep stuff. Go back to the way it was before. So like the offset was like -2 or whatever. That was the old version, the original. And so now it's moving with a constant velocity, right? Let's see, how do I want to do this? All right, so like it's working. Let's change the variable names now, because like I want a velocity variable, I want an acceleration variable. Let's figure this out. All right, so okay. If you think about it long enough, it's offset that controls how fast the ball is moving. Right? If I make this -5 instead of -2, I rerun the program. Ball's moving faster, right? So offset really is velocity. So let's change that word. Right? So instead of offset, I'll call it turtle velocity. All right, so that's that. And then I also want acceleration in the game, right? I need that variable as well. I want acceleration to affect my velocity. So I'll make a turtle acceleration variable. And I'll be like, it could be negative 9.8, but it's really, we're doing this every frame. So it's better to make it a bit of a smaller number for a reason. Otherwise it'll like blow up and speed up too quickly. But yeah, what should these initial values be? Like acceleration, that's what I want for that one. And then for velocity, when you drop a ball, right? It's not moving initially. So initially the velocity should be 0. The initial velocity of the ball. Is 0. And then the acceleration, we're going to have it affect the velocity every frame. So instead of like meters per second squared, the units for our acceleration, for this acceleration variable, are units, like units in the turtle world, per frame. And we're speeding it up, right, every frame. So it's units per frame squared. That's the idea there. So those are those variables. And then all I want to do now, right? The only change is every frame have acceleration affect velocity. That's all I need to do differently. Okay? Every frame have the acceleration affect the velocity. Let me show that to you. So instead of turtle offset, I'm going to change that everywhere, right? We change that to turtle velocity. So I'm going to change that everywhere. Offset, velocity, 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 velocity. Did I miss it anywhere? I think that's good. And then the only other piece of the puzzle is every frame I want to have the velocity affected by the acceleration. So I need to change it. I need to change it every frame. So I'll put this up here. So before we even deal with the velocity, because the velocity affects the position, right? Velocity is changed in position. Before that even happens, we want to have gravity, our version of gravity, affect the velocity. So the acceleration affects the velocity. Oops. And so it's as simple as just like every frame have the acceleration affect the velocity, just like real life. Every second acceleration of gravity affects the velocity of a real life ball. So it's just like your velocity, turtle velocity, was whatever it was, but we're going to have it be affected by turtle acceleration. And acceleration is a negative value because it's pointing downwards, right? Gravity is bringing us downwards in the y direction. It's not like shooting us upwards. So that's why it's a negative value, okay? And so that's really all. So every frame, like we start off velocity at 0 because when you drop a ball, it's not moving at all. It takes time for gravity to affect it. And this will be our gravity constant, -1 units per frame per frame. That's how fast we're speeding up our velocity. And now every time I draw my frame, I'm going to affect the velocity by the acceleration. I'm going to change it and then have velocity do its job of affecting the position. Just as usual. Just every frame you're moving that much. So have the velocity affect the position. We're moving that many units per frame. Have it keep it doing that job and still bounce off. So yeah, acceleration is constant. It's only velocity that's changing always, just like in real life. And honestly, I only added what? I changed the name of variables. I added this line, right? 1 line, 2 lines really. I really just only added 2 lines to this program. Watch. Boop. It's moving a little too quickly for my... But isn't that cute? Just like 2 extra lines, you have gravity, you have real life stuff. So let's make gravity less strong in this virtual world. Negative 0.5 units per frame I think that'll be less choppy of an animation. Whee! That's a bit more like a bouncy ball in real life, I think. Whee! So yeah, you see how it's speeding up as it's getting close to the ground, and once it hits the bottom, once it hits the wall, right, it gets shot off in the opposite direction with the same velocity, but still the gravity is forcing it downward, so it's slowing it down as it gets closer to the top of its arc. Does that make enough sense? That's all physics is. That's how we're modeling the real world. And so I legitimately only added 2 lines to this program. And I got something that looks like a real bouncy ball in real life. Any questions about that? It just seems magical, to me at least. And then also it eventually stops. Like we get that for free, just like real life. Because it's not a perfectly elastic collision, if you've heard those terms before. You got some friction or whatever, keeping the ball down there. Air resistance as well. So yeah, eventually the ball stops. Why? Why does the ball eventually stop? Like it should be bouncing off in the same direction. Like in theory, what we modeled was a perfectly elastic collision. What happened? So first of all, what we did, right? The reason the ball sped up is we had our acceleration variable. It was -1 initially at least. The velocity started at 0, and then on the first frame it went nowhere. But then on the second frame, we had the acceleration affect the velocity. That's what this code was doing, right? We had the acceleration affect the velocity. And so now it's moving at a speed of -1 units per frame. And so that brought the ball down a little bit when we had that affect the position. And then each frame like this is being brought in and affecting the velocity. So now in the same amount of time, it moves double the distance. See that? Now it's -2. And then in the next amount of time, it moves -3 units. So it's being brought down faster and faster and faster every time. That's what our program's doing. And then the reason, it's a fun quirk of our implementation. The reason that the ball eventually stops, the reason that it's not being shot off upwards at the same speed and always bouncing and never stopping, is that this never happens in our program. The ball never actually hits the bottom, because if it did, then it would be fine. The ball actually never grazes the bottom and goes straight up. What really happens in our code, here's what we did to really affect, right? To really affect the velocity. Here's our wall bouncing. This is the bottom wall bouncing. The secret lies in this if statement. Most times, we're not actually going to hit the exact bottom of the window. We're going to overshoot it, right? Our ball was really trying to go down here or something. We never draw it down there, but it's allowed to think about going there, being brought down by the velocity at a certain amount, at a certain rate. So we know we hit the bottom wall if the y ever tries to go down that far, right? And so that's the secret. It really wanted to be here, but what we did in our code was shove it back at just grazing the top, okay? Oops. So what we did is we brought it here, and then we shot it back off with the same velocity that it had when it was kind of down there, okay? So what that does is that, because we're moving it around, that means that the velocity is really getting smaller each time when it gets shot back up. It's not really having the same effect as it wanted to when it really grazed the bottom. So I can prove that to you. You can watch it. I can print out the velocity every frame or something. How do I want to do this? Yeah, let's print out the velocity every frame. Print turtle velocity. You'll watch it gets slower and slower and slower. Because it's clipping through the bottom, and that's the problem. So there it goes. If I stop this, you can see it's getting slower and slower and slower. Apparently the peak, right, the maximum it ever was -19 units per frame, and it never recovered from that. Okay, so that's the secret. So if you wanted a perfectly elastic collision, right, if you wanted it to be shot off at the same speed once it hit the bottom, not at a slightly slower speed, right, because it's always going to be affected by the velocity each frame, and so it'll never get to be exactly what it was, then what you can do is you can hard code that velocity whenever it hits the ground. Just hard code it, shooting back up with +19 velocity now, right, because it needs to change. So if I get rid of this, I'll comment out this line so it doesn't take effect anymore. And so this is the bottom, hitting the bottom of the wall. You're never going to hit the top anymore, given our current program. But what we can do is, instead of this, and just like change the velocity to be negative what it was, because that will eventually clip it out and like not give us the same one each time, let's create a, what's called in physics, a perfectly elastic collision by hard-coding the new acceleration we want, or the new velocity that we want, okay? And so that's saying turtle velocity, when you hit the bottom, shoot back up with exactly positive 19 speed. Does that make sense? Because it was negative, like we would normally change it to positive, but the next frame would kind of mess with that and make it slower than it was before. So that's the secret. If we just hard code this, then every time it hits the ground, it's going to be shot back up with the same speed, and so that means it's never going to ever stop. It's always going to be shot back up with the same speed, and so it'll never get any slower. So it's always going to go just like that, ever so slightly grazing the top there. Does that make sense? Any questions about that? And so this is like a secret number that you have to play around with now if you ever change your velocity, or if you ever change your acceleration, like this is probably not the value you want anymore. But that's the secret. If I go back to the original one where it eventually stops, we can play around with our acceleration, make it be on the moon or something with a lower gravity constant. Ooh. That's fun. But yeah, that's the secret there. I hope that makes a little bit of sense. So we can go back to the way it was. So it will never slow down if you hard code that speed. Always have that speed when you bounce off the bottom. And so it'll never quite touch the top, though. So actually, this code for checking if we ever hit the top is kind of unnecessary with these values, at least. So that's fun to think about. But that's us modeling physics inside of a program. It's really not too hard. It really was just 2 lines, right? Addition of an acceleration variable and having the acceleration affect the velocity. So yeah, if you haven't taken a physics class yet, I'm sorry, but this will make a whole lot of sense once you do. All right. I think that's all that I wanted to say about that. Any questions about this program? All right. So yeah, that's what I wanted to say there. It's a fun example, I think. We went pretty far. The last thing I want to do, because a bouncing ball is very similar to that. So everybody's seen this silly Office episode where it's got the DVD logo bouncing around? That's almost the bouncing ball. Let me show that to you. I need to pause the recording, though, so that I don't get a copyright strike on my YouTube channel. All right, no copyright strikes for me. So what we had, right? That's where we're going next. What we had was this, like a ball moving up and down on one axis. What's the difference between that and this? Well, it's just a square this time, I guess. And it's moving in a 2-dimensional world across both x and y axes, right? In a weird line. And eventually, you want it to hit a corner or something. Bam. But we just need to consider the x-axis now, right? Because we were moving only with respect to the y-axis. The only addition now is change the circle to a square and add the addition of the x-axis doing some stuff. Okay, so that's where we want to go next. It'll take us a couple lectures to get there, but this is a good start. We're going to make a bouncing square. Okay, so here's the game plan. Let's think about it from a high level and then start zooming in and figuring out how to actually program it. Okay. So just like last time, I think it would be a good idea to draw the boundary rectangle, boundary square, so you can see what you're bouncing off of. So that's the first step, step 1. We already know how to do that, right? So check on that bit at least. So draw your screen boundaries. Cool. So that's cool. And then what needs to happen in our program? So we want to make this bouncing square go all over the place. Then we need to create a square. We make the turtle be the square, right? Make a square in some random location within the boundaries. Could go over here, could go down here. Start out somewhere within the boundaries. We'll have to think about what that means, where it could be. Maybe it randomly goes here. And it's always relative to its center. Make its center point go to there, Mr. Turtle, as a square. And then what we did with the bouncing ball is we always started it moving downwards, right? For the square, that's not good enough. We want to move in some random direction around the square, any 360 degree, right? You could pick any of these directions. It should be random. It should be different every time. So we have to figure out a way to encode a two-dimensional direction. That'll be interesting, right? But once we've done that, right, let's say we've picked a direction somehow, we've put it inside of a program, and like this is our direction for our square, a random direction that we've picked. Then, what do, right? We want to move it around just like we moved around this circle. What's the secret? Well, it'll be a forever loop again, forever draw a new frame, but what does that involve as far as the square is concerned? It's, all right, move the square in its current direction, right? However we're representing that. This is going to be our algorithm. Move that square in its current direction if there's nothing in the way. Like right now, there's nothing in the way. It can totally go right here. So move it there. That's what you want to do most times, right? Every frame, move it there, right? So that's exactly the same as the bouncing ball, wasn't it? It's like go in your current direction, like you were moving downwards, go in your current direction as long as you can until you hit a wall. Then you bounce off. That's all we were doing. So exactly the same as the bouncing ball. Instead of going straight up and down, now we're going sideways too. Up and to the right in this case. And so as long as you can, keep going in your current direction until you hit a wall. Like eventually this box is going to hit the wall, right? And then what you got to do is bounce off. So we were moving with that direction, right? We're moving this way. Can't move outside the bounds of the screen. Which way should this ball, not ball anymore, which way should this box bounce now? It should go this way and bounce kind of that way, right? That should be the new direction. So we have to somehow calculate that direction from the old one. Like you wanted to go this way, but we're bouncing off, so now you go that way. There's some math there we can do. But now your new direction needs to be this one. And again, you just keep moving the box in that new direction now, forever, until it hits a wall. So you got this guy, and you keep moving as long as you can until it hits a wall. Boop. Then you bounce that off. And like it was going this way, now it needs to bounce off that way, right? Have to somehow calculate that. And so it'll end up over here eventually, right? So that's pretty much the algorithm from a high level perspective, right? If you were able to do all these things, find a way to make it in code, you see how that would produce this animation that we want? So draw the boundaries, make a square in a random spot, give it a random direction somehow, and forever just keep it chugging along in that direction until it hits a wall, or tries to exceed the bounds of that wall, rein it back in like we were doing with the ball. Just like change the direction to a new direction, right? A new one that's like, it corresponds a little bit to the old one, right? Because like if it was moving this way, you want it to bounce off like that way or something. You want it to bounce off this way. There's like a 90-degree angle there, and that's important. So we'll get into that. But that's the secret. Does that make sense? Any questions about that algorithm? Even though we're not ready to code it yet. You see how if we could, it would give us what we want. So yeah, let's zoom in on all these ideas then. Let's figure out how to do the pieces that we're not so sure about yet. So, well, it's easy to draw the rectangle. We can totally do that. Draw the bounding rectangle, and the turtle can totally turn into a square. Turtle can totally turn into a square. We have the shape of the turtle. I liked him being a turtle at the start. We need him a circle to be the ball, but he could also be a square. So we have that option. So that's fine. And then you could stick him in a random spot by using picking some random integers, right? With our random library. And then, like you can have the turtle, that is the square, could have the coordinates that we use to move things around. But then we have to store that random direction that we pick for the turtle. Like, how do we represent up and to the right in that exact way? How do we represent just like up and a little less to the right? Still same to the right, but still up a little less, right? How do we represent all these different directions? How do we do that? So the secret lies in how we did it before. This was our velocity variable, right? This was moving the ball up and down. Remember that? Up and down, we had it affect the y. So really, this was a variable that affected the y. and so it produced up and down movement. If we just add another variable that affects the x as well, that will produce two-dimensional movement, okay? Like we want to have the ability to move this box randomly, pick a random direction in any of these directions, right? Any degree, 0 through 360 randomly. We want all these bad boys. So how? What's the secret? So just like we stored our, just like we stored our like delta y or whatever, that was our velocity, right? Just like we made that like 1 or something, you can add the addition of a delta x, being like 3 or something. Okay, so that's going to be the secret. Do you see how like this direction, let's see, like if we want to represent this exact direction for our box, we could do it in this way. It's like I want the box to move here next. Like this should be its new center. Do you see how I can represent that idea of moving exactly that way with, I'll use a different color because it's important, by moving a little bit, right? You can achieve the same effect of moving over there by moving a little bit in the x direction and then moving a little bit in the y direction. See that right triangle there? That's the secret. If you move a little bit in the x direction and a little bit in the y direction, that will produce sideways movement. Do you see that? If they're both positive, it's up and to the right. But if some are negative, you're going in different ways. Like this way, right? If you're going in this direction, that means go down and to the left. So negative for both. Does that make sense? That is the secret. Because you could use that now. Like this could be like the delta x, it could be 3, the delta y could be 1. That's kind of what it looks like, right? And that you could use to move the position of your box, because that's all we wanted, right? If the original position of the box was like 1, 1, let's say. This was like the original position of the box. It was at coordinates 1, 1. Okay? We want to move that turtle's x and y coordinate by this direction, which was 3, 1. So, let me get rid of that. Do you see how that corresponds to like this movement of in that direction? Corresponds to moving a little bit in the x by 3, right? Positive 3. And then positive 1 on the y as well. And that'll put this guy right here. And if you have separate variables, like what do? Like your old x was 1, your old y was 1. Well, my new coordinate is, well, the old x plus delta x. And the old y, which is 1 again, plus delta y. So that gives me, like, where I need to move next. That's, well, the old x plus 3 is 4. And the old y plus 1 is 2. Do you see how that'll produce sideways motion? If I just store both ways, right? How much is this direction moving in the x? How much is it moving in the y? Just bring them together. That'll give you sideways motion. It's so cool. So, yeah, we'll store the direction using those offsets, but we just need 2. Because we had 1 for the y before, now we just need 1 for the x. And then the next frame, right? We want to move in this direction still. What should be the new spot? Well, it's just the old x plus the delta x, right? Plus the 3. Plus 3 again, plus 1 again on the y. So that'll turn it into 4 plus 3, that's 7 on the x. And then 2 plus 1, that's 3 on the y. 7, 3. So that's like a profound statement. Does that make enough sense to us? You can store two-dimensional direction anywhere you want to go by storing a corresponding x amount of an offset in that direction and a y amount of the offset. How much does the x change and how much does the y change in that direction you want to go? And that will give you any direction under the sun. They all have a corresponding offset. Like this one has like don't go anywhere for the x but go up in the y. Right? That's kind of what we were doing before. This one was go up in the y but left on the x, so negative on the x. Does that make sense? That's the cool new fact of the day. Okay, so that'll give us bouncing, and we'll get there next time. So we're doing the game plan right now. Okay. The last piece of the puzzle is like we're gonna like it'll just be like all right, pick a random x offset, pick a random y offset. That'll give us a random direction. The last thing we want to do, I think, to make it easy on ourselves for later, is some directions, right? They kind of correspond to speed as well. Do you see how, like this direction with that arrow, and this direction with that arrow are the same direction, right? But one, like if you have this direction affect your box, it's going to move faster than having this direction affect the box, even though it's in the same direction. So they're similar triangles, right? Similar right triangles. Same direction. Like this one's going to make it move faster than this one because it's like a bigger arrow. What we do need to do, and I'll talk about this when we get to the code, is once we pick our random direction, like we pick some random numbers for where we want to move, I think it would be a good idea to normalize, that's the fancy term, to normalize our direction and make sure that that arrow, whatever it was, just keep the direction, but make sure the arrow is length 1, right? The hypotenuse of that direction triangle, make sure it's length 1, because then it'll always move, no matter which direction we pick, it'll always move at a constant speed. That's going to be something we care about later. So that's called normalization. All right, we'll get there. But yeah, that's how you store two-dimensional directions. You just store an x offset as well as a y offset. Okay, that's the secret there. And then we'll implement this next time we have a programming lecture. But the last piece of the puzzle is now, all right, how do we bounce off the walls? Okay, so we had our bounding square. We know how to bounce off the top and bottom walls, all right. It's the same concept. We know how to notice it, but now we have to figure out what do we do, right? So if this was this is like 0, 0, this is a 400 by 400 box, bounding box. So this will mean this is the y equals 200 line. This is the y equals negative 200 line. Those are the bounds, the up and bottom, top and bottom bounds of our playing field. And then these, right, because it's a square, this is x equals negative 200. This is the origin right here. And then this is x equals positive 200. So those are the bounds in which that ball can bounce around, or the box, I guess, can bounce around. That's positive 200. And so now we need to notice, like, how do we know? How do we know when this ball, or this box, hits the wall? Like, it's moving this way with our whatever our direction was. Like, how do we make sure? How do we make sure we know, like, when it's moving this way, how do we know, like, really when it hits this wall? When it grazes it, right? When its direction, because its center is, like, right here. How do we make sure we know still? Okay, so the secret is kind of like this, right? The turtle is going to hit the left wall, right? It'll hit the left wall when the x-coordinate of that turtle, right, is negative 200, or tries to exceed it, right? This is kind of half true because the coordinates are relative to the center, so it's really like negative 200 plus half of its width, but that's not an issue right now. Just pretend it's negative 200. Do you see how if the x ever goes less than or equal to negative 200, it's either grazing that wall or trying to go outside of it. Like if the x over here for the box is less than negative 200, you know, no matter where it is, like it could be up here, down here, down here, you know it's for sure outside the bounds. Okay, that's the secret. And then you know you hit the right wall as well if the x-coordinate for your box is like bigger than negative 200. It's trying to go out here, it's just grazing the wall or something. Does that make sense? So if we check the x-coordinates, we know, like, have we hit the side walls? And we already know about checking the y-coordinates to know if we hit the top and bottom walls. That'll be the same idea, okay? If the y gets bigger than 200, we know it's up here somewhere, right? If the y gets smaller than negative 200, you know it's down here somewhere. We want to make sure it never goes farther, okay? So now the secret is, how do we bounce? Now we know how to figure out if we hit the wall or try to exceed it. How do we bounce off the wall? Because, like, let's say we hit, I don't know, let's say that this was our direction. This is our direction. It was some delta x and delta y. Let me draw this arrow somewhere else. There we go. Let's say that this was our arrow. This is our direction arrow. Delta x, delta y. We want to move in that direction until we hit a wall. And let's say we did hit a wall. We hit the top wall. So here's, like, I don't know. Here's us hitting the top wall, right? We're going in, we're moving there, we hit the top wall. We want to bounce off, right? We want to go in and then bounce off that way. Not any other way. Don't go back this way. We want to bounce off exactly this way. See that? And I guess that's not to scale, but that's supposed to be a 90-degree angle. That's the secret. That's how you know how to bounce off. Okay? So, okay, we wanted to go from that direction to the opposite direction. What is that? Like, we wanted to go this way, right? We wanted to bounce off and then go this way. So that's like this vector. Sorry. You don't know the word vector, excuse me. It's this arrow. So do you see how this kind of corresponds to the same triangle in a certain way? Like this is the one, like this is the new one after we bounce off. This, on the left was the old one. It's still a right triangle. Do you see how it's pretty much the same triangle, like the x, right? The x is still the same. You're still going to the right by x, right? You're starting here, you're going to the right the same amount by x in the x direction. But instead of going to the right and up, when you bounce off the top wall, you want to go to the right and down. Right? You're going to the right and down. So it's still the same amount, though. That delta y, you're still using it. It's just you're going negative whatever the old delta y was. That's going to be the secret to bouncing off a wall. Right? If you hit the top or bottom walls, if you just negate the y part of your direction, you will bounce off in the right way. It'll change this arrow into this arrow. And that's like bouncing off the top or bottom wall. Bouncing off the left or right wall, same idea. So like here's like the left wall. Let's say that like we're coming in this way. Our box is right there, hitting that wall. We want to bounce off, right, this way. And that's going to be exactly what you would expect. Like we came in, going to the left and up, right? That was our delta x and our delta y. To the left and up. Delta x, delta y there. We want to move off, not going left and up, but going right and up. But going right by the same amount. So it's take your old delta x, negate it. It was left, now make it right. Same delta y though. So left up becomes right up. So if you just negate the x offset when you hit the sidewall, that will bounce you off in the right direction. No matter if you're like coming into it from the bottom or coming into it from the top. And so that will do it. That is what we want to program. All right, so let me draw that idea for you because that's the secret. Once you hit a wall, this is what you need to do. All right, so let's say, just for the sake of example, here is my box. It's right here. Here are its exact coordinates right now. It lives at negative 198, 2. That's its coordinate right now. And its direction is this thing. I want to go to the left in the x direction by 2, so negative 2 on the x. And positive 3, I want to go up on the y by 3. So next frame, this box moves right here. Right? It's going to move right to here, and it's going to hit the wall. So it's new spot, right? Because we're going left by 2, up by 3. It's negative 2, 3. It turns the negative 198, 2 into negative 198 minus 2, right? So negative 200. This lives at negative 200, and then it was 2, and we're going up by 3. So it's 200, negative 200, and then 5. Okay, so, it's that special number. We hit the sidewall, we know. We need to bounce off in exactly this direction next frame. This exact kind of direction. You see that? That's where we want to bounce off. That's kind of what we want to do there. And so, it becomes this direction. You use the same numbers. That's the secret. You use the same numbers you were using before. Instead of going left and up, we want to go right and up. Does that make sense? You're going to go right and up by the same kind of amount. This is now, it was going negative 2, now it has to be positive 2, and you're still going up by the same amount, 3. So the negative 2 became a positive 2. That's how you bounce off a sidewall. You negate the x direction. So 2, 3 will take you to, not drawn to scale, I guess. This will take you to negative 198 again. And then you moved up by 3, so it's 8. Okay? So that's the secret there. Any questions about that? My challenge to you is to try to program this before I do it. But yeah, at least you have the bouncing ball with gravity for now. But that's how you bounce off a wall. You use directions by having an x and a y offset, and you bounce off one of the walls. You bounce off the wall that's a side wall by negating the x bit of your offset. The y offset stays the same. You're still going up. You're just like, instead of going left and up, you're going right and up now. All right? So that might take a while to sink in, but that is the secret, and that will eventually give us this bouncing square program, which we will do next time. Yeah. Any questions about that or anything else we did today? That's a lot of cool new knowledge. Whee! So, Yeah, I think that's what I wanted to say there. And that will be the lecture for the day. Let me give you your next programming assignment now that you have all this new knowledge. I would like you to modify the bouncing program, just the normal bouncing without the gravity. So the one from last time. This is the old one. So take this program from not this lecture but last lecture. So start with this program that I gave you. You got the code for it already. So take this program that I already gave you, right? Just with the constant speed ball and mess with it. So this is what your next program assignment is about. I want you to mess with this program that I wrote for you before. So take this program, and what I'd like you to do is the following. You're gonna have the ball bounce, and the walls are magical. All right, that's the trick this time. So write a Python program that does the following. All right, so I've done all of these things for you up here. Draw that bounding square to represent the walls, and make an animated ball bounce up and down. So that's the first part. And then what I want you to add is every time you hit a wall, every time the ball hits one of the walls, you know where that code is, right? You'll hook into here, right? Every time the ball hits one of the walls, those are those if statements. Every time the ball hits a wall, I would like you to make something weird happen randomly, because the walls are magical, okay? So here's some ideas for you. Like maybe when the ball hits a wall, change the color of the ball to something random. When the ball hits a wall, change the size of the ball. Stretch it out by a factor of 0.25 and 4. I've done all of those before, right? Fill color changes the color. The turtle size, you give it an offset. It'll mess with it. So you can do that. If you want a random floating point value, use random.uniform to do that. So look into that. You can, every time the ball hits a wall, or randomly, you're choosing among these options, kind of, right? You'll pick your own options, though. You can change the x coordinate of the ball to a random one, like make it teleport to the other side of the screen as it hits the wall. You can change the speed of the ball by some random factor. Like the speed of the ball is in the turtle offset variable, right? So you can change that to something random, multiply it by a factor. You can also, maybe every time you hit a wall, maybe you can change the shape of the turtle. Like that's your magical effect. Change the shape of the turtle to do something other than be a circle. Like make it a normal turtle when it hits the wall. So every time the turtle hits a wall, I'd like you to make something weird happen, and I'd like you to choose randomly from these things. Like, you don't have to do all of them, but like it shouldn't just be like always change the color every time. You should make it pick some from like 3 of these random ideas, kind of. Okay? So that's your next requirement. I'd like you to make a function. This is me forcing you to make a function, okay? Please make a new function called do something weird or something similar to that name. Just a new function with the name of your choosing. And that's what I want you to call whenever you hit the wall. All right? That'll be the thing that randomly picks a weird thing to do to the turtle and does it. Okay? So you'll call it every time your ball hits the wall. And I'd like your program to like shuffle between at least 3 different weird things that happen every time your ball hits the wall. Right? Like you can choose 3 of these options or pick 3 of your own, whatever you're into. Okay? So your do something weird function should like flip a 3-sided coin essentially every time and like figure out, should I do this weird random thing or should I do this other weird random thing? Because I know I just hit a wall. Okay? So you're going to hook in to these if statements, because that's when you know hit the wall, and you're going to have it call your new function, and that function will choose something random to do. Okay? Does that setup make sense? So I'm forcing you to make a function. That's what this programming assignment is about. All right? So you can reuse most of my code. Here's a hint to pick between, like, let's say you want to pick between 5 weird things to do randomly. So here's what you can do in your code. You want to pick a number. Like the secret is, like, pick a random number between 1 to 5, set it into a variable, and then use a big long if else. If that random variable was 1, do that first weird thing that you were thinking about. If it landed on a 2, do the second weird thing. That'll be my hint to you. Okay? And so, yeah, turn in a video of all that happening, and I've made a fun little GIF. That's like an example of what your program should do. So here's kind of what should happen. Every time you hit a wall, do something random. Like it changed the shape. This time it changed the speed, changed the color again randomly, changed the speed, shape, warped it, changed the X location, changed the speed, changed the color, changed the size. So that's kind of what I want you to do. Does that make sense? Every time the ball hits a wall, the walls are made of magic, and I want you to do something random every time it hits a wall. By calling your function, though. Okay? There, it changed into a turtle. Cute. So, yeah, any questions about that? This is kind of what I want to see, but you don't have to do as many weird random things as I did. You can pick just 3, but as long as it's a minimum of 3 options every time you hit a wall to choose. Okay. Questions about that? So use this as your guide, maybe. But that's what I'm looking for. Okay. So there's a lot of moving parts, but you're really just hooking into right here these if statements because that's when you hit the wall. You're going to call your function, have it do the weird random thing, right? And choose from at least 3 weird things to do each time. Yeah? Does that make enough sense for now? So this will be due week 16, so you got a little while. And I think that's all that I wanted to say. So yeah, record a video of you explaining your code. Show me all the cool, weird things of your magical walls as it bounces. And yeah, I think that's all that I got for the day.